some randomness, because we don't know the measurement outcome before the measurement, and the evolution by measurements is not unitary, it's not reversible, it's a projection. So consider then a set of local observables, which we term M, and say we measure these and say that their number is proportional to the dimension of the system, and we measure those operators M. And if we have no Hamiltonian and all these measurement operators commute with each other, then what happens is that after a sufficient number of measurements, the wave function will just collapse onto a joint eigenstate of all these measurement operators. However, if we then switch on a Hamiltonian, which does not commute with all the measurement operators, then they don't have a set of shared eigenstates. And what will happen is that this time evolution, having a Hamiltonian and performing measurements, will never come to a rest, because there's just no shared set of eigenstates at which the evolution would terminate. And this is kind of a familiar setting that we know from many-body systems, actually. If we consider a many-body Hamiltonian that is composed of two pieces, H1 and H2, which are not commuting, then this means they don't have a shared set of eigenstates. And the ground state of this system, if we switch off the second Hamiltonian, will just be the ground state of H1. If we make G infinite this coupling, then it will be the ground state of H2. But in between, the competition between the two will lead to a quantum phase transition. And we will try to identify a similar scenario with measurements here. So where this H2 is replaced by performing measurements of a set of operators. But we already see here kind of a big difference, which will be important, because if we're performing measurements, we can collapse, or performing measurements will push us towards one of the many different eigenstates or measurement eigenstates. Yeah? So there's a large manifold. So we don't know where we end up, while in a quantum phase transition, typically there's a small manifold of ground states. And so the configurational entropy is very small, while for measurements, you can have many different states that are compatible with a stationary state. Okay. And this scenario of having a competition between unitary dynamics and measurements has recently gained a lot of attention in the many-body context. And I would like to start with the initially proposed setup that people had in mind. And there they were just saying, let's consider a one-dimensional system, and we start in some product state where, let's say, on each side we have a well-defined state, and we then take the product, and then we perform an evolution where we apply unitary gates which entangle to the neighboring sites. These are these green blocks here. And so if we do not do anything else, then what happens over time, the system will become strongly entangled, and we will build up a volume law entangled state over time. However, between these gates, we can now apply measurements, local measurements indicated by those dots, which project the system back towards a local product state. And now it depends on the rate of measurements compared to the unitary gates, what this state actually will be. So as I said, if we don't make measurements at all, we're ending up in a strongly entangled state, which shows a volume law entanglement. However, on the other hand, if we measure a lot, if we measure constantly, then there will be no way how entanglement is built up, and we will end up just or stay in a product state forever. You know? And what these works here found out is that there's actually a phase transition between these two regimes. So there's not a crossover, but actually there's a sharp transition between a phase where you have a volume law entanglement in this setup and a phase where you have area law entanglement. And in this case, kind of your wave function resembles that of a generic kind of many-body wave function, while here it's just a product state. And we would like to understand better the nature of these phase transitions and how one can be able to use these scenarios, maybe, for instance, in the context of state preparation or quantum error correction. And the particular situation that we will discuss here is a model, very, very elementary model of just having a fermion chain without interactions, just having fermions hopping on a chain, and we're continuously measuring the fermion density locally. And what we identify in this model is actually a new type of entanglement transition, which is different from the one I just outlined. And then I will discuss our analytical understanding, where we find that this is actually a pinning phase transition, which corresponds to the Berezinski-Kosterlitz-Thouless universality class. And just let me start discussing the elementary competition that we are considering. So we really have a very basic Hamiltonian. We have non-interacting fermions hopping on a chain. So we have some Hamiltonian, which lets fermions hop to neighboring sites. And we are performing measurements of the local particle density. So we ask, what is the particle number at a given site? Is it 0 or 1? And to understand this competition, we first focus on the two limiting cases. Let's say we only have Hamiltonian dynamics. In this case, if we have some hopping with some rate j here in the Hamiltonian, the dynamics is fully deterministic. If we start with some initial Néel state, which is just this product where we have 0 or 1 particles at each side, then under this time evolution, any initial pure state remains pure, of course. And if we evolve the system for a sufficiently long time and then take a bipartition of the system into two halves, A and B, where A scales with the system size, and compute the entanglement entropy, what we will find is that actually we find some volume law entangled state. So we have an entanglement entropy that scales with the system size. On the other hand, if we are considering only measurements, no Hamiltonian, and now I have to be a little bit specific. So what we consider as weak measurements, so we're not considering direct projections, but actually we have a weak or continuous measurement scenario in mind. And that means we are not directly reading out the local particle number, but actually we have this local particle number operator coupled to some auxiliary system, and we read out the auxiliary system. And for now, I don't want to go into the details. I don't know, maybe Alessandro will do that in the talk after mine. But what you can imagine is just the following. Instead of doing an immediate projection onto an eigenstate, you will need some finite time, 1 over gamma, in order to project your system onto an eigenstate. So you have some exponentially continuous projection onto an eigenstate. And the dark state of this, or the asymptotic state of this pure measurement evolution will then be, again, a product state where each lattice site has a well-defined particle number, such as this Néel state, for instance. And so if we take a bipartition of the system, then the entanglement entropy will not scale with the system size or the size of the bipartition, because we are just in a product state. So it will just be constant, in this case, 0. Okay. So what happens if we now put these two situations together? So we have now an evolution where we have Hamiltonian dynamics with this tight binding model, and we're having this continuous measurements. And now after a certain time, we produce some wave function, and this wave function is a random variable because it depends on all the measurement outcomes that have previously been occurred. And these are randomly distributed. You have some finite probability for all these measurement outcomes. And so if you want to say, well, what happens? I take a measurement at some point, but in order to make sense of this measurement, I have to average over all the measurement outcomes. And if I'm doing that, then what we will see, because of this large randomness, actually the linear average of the density matrix or the total ensemble average will just be a maximally mixed state corresponding to some infinite temperature state. So it does not contain any information about the individual wave functions. And this can also be seen if you just look at the linear quantum master equation for this density matrix. See, you have a Hamiltonian part, and you have this double commutator with Hermitian jump operators. If you insert a unit matrix for rho, this will just solve the equation. This will be the stationary state. So the question here is, how do we access properties of instantaneous wave functions? Because as I just said, we expect that depending on the measurement rate, these wave functions will look quite different. And the solution is to examine the properties of the state before doing the average by looking at nonlinear observables. And what is a nonlinear observable? For instance, if I'm looking at this connected correlation function over here, then this guy is a linear property of the state, but this guy over here is nonlinear in the state. So it involves two copies of the state and therefore has more information than kind of a linear average. And the same is true if I'm looking at the von Neumann entanglement entropy of a given wave function and then average over all these von Neumann entanglement entropies, I will get a different information than of just taking first the average and then computing the entanglement entropy of this. And indeed, if we're doing this, what we find is that there's a new scenario where we actually don't see volume law growth of the entanglement entropy or an area law, but actually we see a logarithmic growth of the entanglement entropy if the measurement rate is not too strong. And this is reminiscent of a conformally invariant phase, or at least scale invariant situation that one encounters at the quantum critical point, for instance. So we want to understand this better and look at the phase diagram of the model. What we're doing is, this is a quadratic system, so it's easy to simulate. We simulate these wave functions over time and then compute the entanglement entropy and look what is the behavior of the entanglement entropy. And what we find is this type of phase diagram over here, where in the thermodynamic limit, where the system size goes to infinity, we actually see an extended regime of sub-extensive scaling of the entanglement entropy, which is really reminiscent of a conformally invariant phase at weak measurements. And this phase is connected to volume law behavior that we already discussed for the pure case, where we only have Hamiltonian evolution, but this occurs only at zero measurement rate in the thermodynamic limit, and it has a finite size crossover to this critical phase at finite system sizes. On the other side, if we increase the measurement strength, so if we measure more often, more frequently, then at some point, what we already saw will happen, we will see a collapse onto a product state, or effectively a product state at large distances, which has an area law entanglement. And this is separated by this sub-extensive critical behavior by a phase transition at the critical measurement strength. So in order now to better understand this regime here, where we see this sub-extensive scaling and the phase transition, we look at the set of different observables that we can simulate. First of all, we are looking at the entanglement entropy, and we fit the entanglement entropy in this weak measurement phase to this Cardi-Calabrese formula over here, which predicts the scaling of the entanglement entropy in a conformally invariant system. And what we see here is actually this fits very well, this expression, except that this prefactor C, which is usually in a conformally invariant system, the central charge of the theory, is actually here a measurement dependent number, and it decreases with the measurement strength. So if for weak measurements, this decreases algebraically, like 1 over gamma, 1 over the measurement strength. But if we come close to the critical point where we saw this transition, actually it decreases exponentially in gamma, which is reminiscent of this Brzezinski-Koselleck-Staulis scenario that I mentioned before. Furthermore, we're looking at these connected correlation functions that I mentioned. If we investigate those, which are nonlinear in the state, what we'll see is that for weak measurements, they are scale invariant. They decay like 1 over the distance square. While if we increase the measurement rate, we will see that they become exponentially suppressed with the distance. So this also fits kind of in the picture where we have an emergent correlation length in the area law phase. And finally, in order to really test conformally invariance of the system, we look at the mutual information over here, which we plot. So this is kind of the mutual information between two subsystems A and B, which we look at as a function of these randomly chosen boundaries here. And for a conformally invariant system, the mutual information should only depend on this cross ratio eta and not on the precise form of A and B. And we see this very nice scaling collapse over here for the mutual information, which kind of confirms to us that this is indeed a conformally invariant phase emergent at weak measurements. And this is kind of a very interesting story, because the only ingredients that we put in is a very simple Hamiltonian, particles hopping on a chain, no interactions, and measurements of the local particle density. And for weak measurements, this leads to kind of a new phase that displays all nice signatures of conformal invariance. And yeah, as I said, the phase transition between the two regimes looks very much like a BKT transition. Okay. So now we would like to understand this numerically observed scenario, kind of an emergent conformally invariant phase and a phase transition better from an analytical perspective. And therefore, we will now try to understand the emergence of this phase and its signature from an effective field theory that we derive from the microscopic evolution protocol. And before we go again into more details, let's focus on the most simple toy model, because this tells us already a lot about the physics in this model. So let's just consider a single fermion hopping on two lattice sites, between two lattice sites. And if we're doing this, we can trace as a function of time for a single trajectory, the probability of finding the fermion on the left or on the right side. And what I'm plotting here for different measurement strength is actually the time evolution of this probability of finding the fermion on the left side. So we see if the measurement rate is large, so if we're measuring a lot, the fermion actually hops just between it. It's pinned for a very long time to one of the measurement eigenstates. So the probability of finding it on the left side here is almost 1 for a long time. And then it suddenly jumps to the other side. So it remains pinned for a long time in the measurement eigenstates and just performs sudden jumps between these eigenstates. On the other hand, if the measurement rate is weak and if the Hamiltonian dominates, what we see is something like noisy Rabi oscillations, where most of the time the fermion actually spends in a superposition between the two lattice sites. And so that's kind of our picture that emerges for this type of transition, that we say in the thermodynamic limit, we will have a phase transition between a situation where fermions are delocalized over the lattice, and this gives rise to this conformally invariant phase. And on the other side, we have an area law phase where the fermions are pinned to their positions. And now we want to derive a minimal continuum model in 1+1 dimensions, which explains this and allows us to discover or explore this phase transition. And for this, what we need, because we already saw that all this information is encoded in these nonlinear observables, what we need is actually a theory which considers several replicas of the system and not just a single density matrix. So first, the minimal continuum model that we consider that has the basic competition built in is Dirac fermions in a 1D on a 1D wire. And we have this Hamiltonian describing fermions propagating with a linear dispersion. And what we consider is measuring these two operators, O1 and O2, which are the two fermion densities essentially that you can construct. We can bosonize this model and then see the Hamiltonian is given by this Latinger liquid Hamiltonian, and the two measurements operators are given by this current operator and this vertex operator over here. And if we just look at the measurement operators, what we see is the eigenstates of these measurements are again product states where at each position I have a well-defined density phase phi. But on the other hand, the Hamiltonian does not like these states because there is this non-commuting field theta over here and wants to delocalize this density field. So it has essentially the basic competition built in that we need. We have some measurements that want to pin the system onto certain eigenstates, and we have a Hamiltonian that doesn't allow for this pinning. And just to remark, this is also the kind of naive continuum limit and bosonization of the lattice fermion model, but we don't want to kind of be too precise on this connection. Okay, so now having this continuum model at hand, we have to generate or construct a replica field theory to describe the dynamics. And I mean, this is some standard approach for disordered systems where you have randomness in your system. But I would like to motivate this also by our observables that we looked at. So we said that in these connected correlation functions over here, which are nonlinear in the state, we can see this entanglement transition. So we can see this phase transition. This should be scale invariant as a function of the distance if we are in this weak measurement phase, and it decays exponentially if we are in the strong measurement phase. So written like that, it is nonlinear in the state, but we can write it as a linear property if we introduce replicas in Hilbert space, where we now say we consider a joint wave function, which is just a replica product of two individual wave functions, which both describe the measured fermion chain. And then in this case, all quadratic observables are encoded in this property here, in this two replica density matrix, which we can then linearly average. So this is now a linear average over this, but of course it contains the different replicas. So, and if we're looking at the quantum master equation for this, actually this should be two, for this two replica density matrix, what we will see is that we get an evolution equation for each individual replica, namely the Lindbladian that I discussed in the beginning, where we said this just leads to an infinite temperature or to a maximally mixed state for both replicas, but we get an additional piece that would not be here if we're not considering replicas, which is a term that couples the different replicas by measurement. So this is really the important step. We get this additional contribution here, which introduces a replica coupling term. And now the evolution is no longer diagonal in the replica index. But we can make it diagonal again by introducing a new set of coordinates, namely an average coordinate now expressed already in the bosonized fields, where we said we have an average coordinate, which is just the sum over the two replica fields. And we have a fluctuation coordinate, which is the difference of the two replica fields. And the nice thing is that this sum term now accumulates all the configurational entropy. It accumulates all this mixedness. So this coordinate becomes totally mixed, or the density matrix for this coordinate, but the density matrix for this coordinate actually becomes pure. And that is what I would like to show you. So if we're looking at the master equation for these individual terms now, for this average mode and for the relative mode, we see this average mode indeed again heats up to an infinite temperature or a maximally mixed state during the time evolution. So this contains no information on the state. However, this relative coordinate evolves according to a non-Hermitian Hamiltonian and therefore cools into a well-defined and actually pure state. And the pure state is a dark state of this effective Hamiltonian over here. So in this effective Hamiltonian now is a non-Hermitian Sine-Gordon Hamiltonian, and it has again kind of the competition built in now in terms of complex couplings, where we have this term here, a nonlinear term, which wants to pin the density field corresponding to pushing the system into eigenstates of this density field. And here a part where we see that this phi field wants to delocalize or wants to make this phi's fluctuating. And we can now extract the physics or the phase transition in this model from a path integral approach, which we do. So this is the corresponding action, which now has complex couplings k, eta, and lambda. It's not so important what these values are actually, but it's important what we can extract from this action. Namely, we have two limits. One limit where this lambda term here, this nonlinearity, is irrelevant, and we come back to a quadratic theory. And in this quadratic theory, what we find is we can compute scale invariant correlation functions decaying like 1 over distance square, which matches our prediction from the numerics. And in the limit where this cosine becomes relevant, we get exponentially decaying correlation functions. And the phase transition separating these two regimes is actually of the BKT type. So it corresponds to the BKT universality class. And this is all in line with the numerics for the lattice fermions. We can extract this effective or this prefactor of the logarithmic entanglement growth as a function of the system size, and it matches with a prediction that one would expect in a BKT scenario where it jumps from a finite value to 0 at the phase transition in the thermodynamic limit. Okay, so I will just be very brief. We also looked at the system for long-range hopping, where we now, instead of just having nearest neighbor hopping, we have hopping over many sites with an algebraic amplitude that decay, or with an amplitude that decays algebraically. And there we find a new scaling behavior, a new type of phase transition, where the entanglement entropy now does not scale logarithmically, but actually it scales with a power law, but with a varying exponent that depends on the exponent of this hopping term. And this also, if we're looking at this, we have here numerics, which are the crosses, and we're having the field theory prediction, which are the dashed lines, and they match really perfectly for this setup. So we think that our basic field theory or our basic replica theory actually really covers what's going on in this system.
I'm sorry, could you go to conclusion?
Yes, sure. Yes, we are at the conclusions. So yes, what I told you was I presented some numerics for measuring free fermions on a chain, and we saw that just by adding measurements, we actually spice up this system and spice up the dynamics of the fermions. And what we find is that for a finite but weak measurement rate, we find a new phase described by scale invariant or conformally invariant observables. And this phase is interrupted or is destroyed by increasing the measurement rate, where we find a BKT phase transition into an area law phase, where the system on large distances just looks like a pure product state, which we expect from just measuring the particle density and having no Hamiltonian in the system. And the kind of interesting thing here is this decomposition to understand how there effectively emerges quantum dynamics in this system, namely in these relative coordinates. By splitting the system in relative and absolute coordinates in this replica formulation, we find kind of quantum dynamics for the relative coordinate and this heating of the absolute coordinate, which accumulates all this measurement randomness. Future directions would be to check how we can actually experimentally observe this. And this is not an easy task because, as I said, each wave function is a random number. And usually you need many experiments in order to get something like an expectation value. But if each experiment generates a different random number, it's very hard to extract properties of individual wave functions. And yeah, also kind of trying to understand if we can apply this approach to other type of entanglement transitions. Okay, that's what I want to say. Thank you very much.
Thank you very much for the talk. Let's thank the speaker. Please, does anyone have questions? Okay, Yuval.
Okay, I have a couple of questions. The first one, can you go back to your slide with the example of Rabi oscillations with strong and weak right? So I would expect that even if I'm in the limit of a weak measurement, if I repeat this measurement again and again and again, it will add up to a strong measurement. So yeah. I am a bit surprised that even at relatively long times, the Rabi oscillations still persist and are not destroyed.
Yeah, so what you can imagine, I mean, if let's say we would do a strong measurement at a certain rate. So what you would expect is you start on a well-defined site, and then you have Rabi oscillations, and then at some point you measure, and this measurement gives you a collapse onto one of the eigenstates. But then you start from this state again, and you perform again kind of Rabi oscillations. So this would be a strong measurement where you can say you complete several Rabi oscillations between different measurements. Now for weak measurements, you do not extract this full information. Yeah? So this is really just an individual trajectory. So this is just one trajectory. If I'm starting to average over this, if I'm averaging over many trajectories, exactly what you say is happening is I will still say, because if I'm starting always with the same state initially, I will maybe see two damped Rabi oscillations, but then I will be just stuck in the middle. So I will always be stuck at 0.5 if I'm doing this for long enough times. But this is just for one trajectory.
Okay, fine. Thanks. I mean, and the second one, you spoke or you showed that the effective evolution corresponds to a non-Hermitian Hamiltonian. Yes, I mean, maybe you can put a slide with the non-Hermitian Hamiltonian.
Yeah, this one.
Yeah. So I was not able to follow all details, but I know that in principle, in order to go from Lindbladian or Liouvillean dynamics to a non-Hermitian Hamiltonian, I need to do some sort of post-selection.
Yeah, no, this is
where is this post-selection here?
Here, I mean, this is not really a physical coordinate. So what happens, and this is really a nice thing that we observed, is we go to this replica formalism, and now you can imagine each of these replicas. So you have system 1 and system 2. They both have this evolution, this stochastic evolution, and now by averaging, you see that both of these replicas get these usual averaging terms, like the Lindblad evolution, and then they have this replica coupling, which is a weird thing. And now we introduce a new set of coordinates, kind of by doing something like a Fourier transformation in this replica space. And there, what you see is kind of, if I'm looking at this average value here, I see these kind of these effective Hamiltonian terms are completely absent here. So I'm just having the two recycling terms acting on the density matrix, while in this relative coordinate, I just get this effective Hamiltonian terms. So there's no term which acts on both sides. And so each individual density matrix doesn't make to look sense at. We have to always see this as a product where this guy heats up and this guy cools down. But then there are several observables which are susceptible to this one. And exactly this connected correlation function is one where this is the case. But there's no approximation where we throw away this recycling term, but actually it is in this effective description, it is split between just this only having recycling and this only having cooling over here.
Okay, thanks.
Alessandro?
Yeah, first of all, very nice talk and very nice work. I really like it. I have a question about the measurement operator you introduced in the continuum in your yes. So my question is, why do you need to introduce two operators? And I mean, is this the only? I mean, is this the exact continuum limit of the lattice model that you?
I mean, it's a very good question, and we are still trying to figure this out. And this was actually the starting point. Of course, what we would like to say is we start from this lattice model and then just bosonize it. But you can't just do this, right?
Yeah.
So you have to, for instance, somehow a posteriori, we can say, well, we see that this replica coordinate goes into some effective ground state, and this justifies before that we did this bosonization. But the bosonization directly on measuring this chain is so far not really justified yet. And therefore, what we did in this paper is to say, let's take this model where we know how to treat it and say, maybe this is a good approximation for the lattice model, which I think it is, but I can't at the moment only a posteriori, and then make this choice for these two measurement operators essentially here.
Yeah, let me follow up with very quick, because your operator O2 has a parameter M that controls somehow the strength of it, together with gamma, which I suppose appears in front of both operators, right? But the operator O2 is essential for you. If you just so Hamiltonian, if you put M equals 0, you essentially don't
exactly.
get
So we need both of them. So we need both of them. If we're not having O1, then there is not there in the scale invariant phase, we don't have any cooling effect. So this generates this cooling onto this guy, generates this cooling onto this conformally invariant phase, which would be absent if we just have this measurement operator. But on the other hand, if we're not adding this, we're not getting the phase transition.
Yeah, so that's fully agree with the way I understood your work. Just one last comment. Numerically, do they agree? I mean, you can calculate your transition point in terms of gamma over V, I suppose.
Yeah.
From the theory, and you also can numerically determine from your lattice model. Do they agree numerically, quantitatively?
I mean, they agree, let's say, in the order of magnitude. But I mean, as you said, this parameter is always, as far as I know. I mean, also in the high energy kind of papers, this kind of parameter is not really exactly known, precisely known, typically this M for the bosonization.
Yeah.
So and if we set this to 1, then both transitions are appearing at gamma of order 1. You know? So and if we just say J is V here. So that's kind of, I think in the numerics it's 0.8, and here in the analytical model it's really at 1, gamma equals 1.
Thanks.
Okay, one more question I see.
Yeah, very nice talk. I have one question about, you study fermions. What about a 1D boson chain with, let's say, repulsive interactions? If it's a completely Hamiltonian system, it also maps on the Latinger liquid. So the question is, your measurement scheme, can it also be accounted for in the bosonization? And in other words, do all the results just carry over to interacting boson chains?
Yeah, this is a very good question. And there's one thing. So we think, let's say, if you have a model that is amenable to bosonization and that you can exactly bosonize, so there are no residual terms which you would throw away and say they are in some sense RG irrelevant. If you really have a perfectly integrable model, then I think we can carry this over. The problem actually is when I'm going to this point here, we want to make a decomposition like that, where we say this absolute mode decouples completely from the relative mode. And if we're having some terms that even in the slightest way break this decomposition, then we will kind of have that this heating of the absolute mode will kind of be carried over to this relative mode. So in the same sense as if you have a model that you can describe very well in the ground state by a Latinger liquid, but if you add a little bit of interaction would thermalize, in the same sense here, this situation would from our understanding now break down. So if you have a perfectly integrable model, we think it behaves the same way. If you have a non-integrable model which just maps in the long wavelength limit for ground states to a Latinger liquid, then I think the story is more complicated.
But even for fermions, you usually have correction terms like from nonlinear dispersion and so on.
Exactly.
But these are harmless for fermions, but dangerous for bosons, or it's not so
I mean, it depends also on the terms. So this nonlinear dispersion term, actually, I think it matters. And that's the reason we think right now gives us this finite size crossover over here. So we see at small distances, we see this volume law phase, but this behavior is still nice enough to, in the thermodynamic limit, kind of be eliminated. But I think this curvature, if we, for instance, artificially in the numerics make a linear dispersion, which is hard to do, but we can do that, then this part, this volume law part, is shifted much closer to small gamma.
Okay, thank you.
Okay. Thank you. I have also one small question or comment. Can one say that the similarity with Latinger liquid model in continuous limit is connected with the fact that your study the quantum dynamics, the joint quantum dynamics of your chain entangled with measurement, which is entangled with all, not entangled, which is governed by a measurement operator which measures all charge states. So it seems that your measurement operator gives uncertainty in charge states. So due to Heisenberg fundamental uncertainty relation, you should obtain in some step phase coherence, which means that your measurement gives you complete uncertainty in charge, but complete certainty in phase. So you have phase phase coherence, which can be translated into the language of entanglement.
So what I think is, you're right in this sense. I really think in this phase, we have actually states that have phase coherence over large distances. The problem is that the overall phase, and also kind of locally, there's some randomness you have to add. And so all the wave functions look a little bit different. But if we're looking, for instance, if we're looking at interference patterns, we see that there's a state which has phase coherence over large distances in this phase, and in this phase there's not. But what I think, where is the origin of this Luttinger liquid coming? And this is kind of, I only have a hand waving argument, or kind of a high level argument, is to say, in this phase, we understand what's happening in this area law phase. We're projecting onto this product state, right? And the Hamiltonian is not strong enough to kind of remove us from this product state. In some sense, we're extracting so much information from the state that the Hamiltonian is not able to destroy this information. So we always know where the particles are. And now entering this phase, what happens is still we are cooling in some sense by extracting a lot of information from the system by measuring these local particle numbers, but the Hamiltonian is now strong enough to mix the state faster than we're extracting this information. But because we're kind of extracting all this information, we do this effective cooling towards the most simple state that we can imagine here, which is kind of this lock state. I hope this answers kind of your question.
Okay, thank you. So now we should move to the next talk. And it's my pleasure to introduce the next speaker, Alessandro Romito from Lancaster University, United Kingdom. Entanglement, the talk is called Entanglement Transition from Stroboscopic to Continuous Measurements in Interactive 1D Systems. So Alessandro, you're welcome. 30 minutes.
Thanks. Thank you, Gleb. Let me see if I can share the presentation. Can you see the slides?
No, we don't. Oh, okay, now it's okay.
Now you do?
Okay, we see. We see your slide.
Perfect. And you can hear me well, right?
Yeah.
Okay.
Everything.
So thanks. Thank you, Gleb, for the introduction, and let me also thank Kirilo for inviting me to this very nice conference. My talk is essentially the same topic as the previous one. It's just we're looking at the same kind of transition, but in a different model. So we would see that the transition has different features. I will also have some overlapping introduction with the talk by Mikkel before. I hope you don't mind. We'll have a different take on some of the introductory aspect to this entanglement transition. Specifically, the work I'm talking about is a couple of works in the past couple of years, which have been done with some of my collaborators here in Lancaster. Let me mention two names in particular. Marcin Siniski was postdoc involved in 3 of them, and now is in UCL. And Tobias Bormann is a master student of mine who moved to St. Andrew last year. Good. So let me start. Slide. Yeah. So I'll start from a simpler case, which is the competition between Hamiltonian dynamics and measurement dynamics in the simplest setting that we know, which is just a 2-level system, single degree of freedom. And this is Zinn effect, quantum Zinn effect. So what you see here is, can you see my pointer on the slides? Well, I hope you do. So what you see here is a spin, which I represented in a block sphere. And you consider a system subject to a very simple Hamiltonian, just coupling to Sx, which induces quantum oscillations between 2 states, spin up and spin down. And what we add is measurements, and here I'm starting from a very simple case of projective measurement. So at regular intervals of time delta t, I project system, the spin, either in the z direction. So I will either project and spin up or spin down. Schematically, you can think of this system in this circuit model that I will use later. So you have time goes by and you have some unitary dynamics, which are the oscillations due to the Hamiltonian. Then you project with this yellow matrix M, which stands for measurements, and you repeat it. Now, if you want to ask what happened to the state of the system, you can quantify it by the probability to be in the spin-up state. So if you're just running the Hamiltonian, you will see oscillation, which is this wave part of the curve you see in the picture here. Now, if you measure at interval dt, what you see is that this evolution, the starting of this oscillation, is interrupted by measurement, and you either project it to p equals 0, which means spin down, or project it to spin up back. Now, the probability to be projected in each of these two states depends on the state itself. So what will happen is that because it started close to spin up, it will most of the cases be projected up with high probability, and only very rarely will happen and it will be projected down, so you will see a big jump. Now, the same effect has to do with the fact that when dt goes to 0, essentially the system remains frozen around the spin-up state, simply because when dt goes to 0, the probability of this large jump is shifted to infinity, so this large jump to spin down will happen more and more rarely. So this is the simplest example in which we see unitary dynamics, competition between unitary dynamics that tries to induce quantum oscillations, the spreading of the state, and measurement that try to localize the state to one of the eigenstates of the measured operator. Now, the question we're asking is also a question of, in general, is entanglement transition has to do what happened to this kind of physics when you go in many body settings. So the most immediate generalization of the example before is just to consider a spin chain, which has some local interaction between spins, and you also want to consider local measurements. That's the only constraint you typically have. So if I represent this as a circuit, you see now these horizontal lines are the time evolution corresponding to each spin, and you have this purple bluish block are the unitary evolution associated to the dynamics, and this is intercalated by measurements. Now, the question becomes more interesting for many body systems because, of course, if you measure frequently enough each of the spin, you will still localize all of them into spin up, spin down configuration. But the question that arises in many body systems, something that is not there for single particles, is about the transport of densities like excitation particles or information across the chain. So is there a cutoff and a transition between a regime in which the unitary dynamics led all this quantity to be transported across the system and measurement that localize this kind of densities? The question, let me put it in a bigger context. It's not just an academic question. It has to do with the way in which we understand thermalization or periodicity in quantum systems. So quantum systems are not periodic in the classical sense because they are quasi-periodic, so you never reach an ergodic phase. So you cannot thermalize the same way classical systems do. So the way we understand thermalization in a closed quantum system is by spreading of information across the system. So what you see here is just single excitation depicted in red, which due to the Hamiltonian, or if you want the unitary dynamics, in generally spreads across the whole system. And what happened in this context is after a sufficiently long time, if you look at any small subsystem, this subsystem looks in fact thermalized. So the way we understand thermalization is by the fact information spreads across the entire system, and local subsystems show an equilibrium distribution like a Gibson sample. So this goes under the name of eigenstate thermalization hypothesis, but I'm not entering into this kind of physics. The only point I want to make is that this behavior in which information is spread and each degree of freedom is correlated with each other degree of freedom across the system is characterized by the volume law scaling of the entanglement entropy, which is a measure of information, if you want. The other thing we know is that there are general patterns in which this kind of thermalization behavior is broken, and the most known famous one, also probably the most general one, is the one of many-body localization. In this case, is due to static disorder. So if the chain is disordered, what happens is that this pattern is broken, and the effective description of the system happens in terms of localized degree of freedom. So what happens is that the excitation do not spread across the chain anymore, but are localized in patterns of few degrees of freedom. And as a consequence of this localization, the information doesn't spread across the entire system anymore, but rather the entanglement scales as an area law. So these are huge fields. I'm not going into details here. The only take I want to get from these studies is that the unitary dynamics is associated with the ergodicity and volume law scaling of the entanglement entropy, while there are patterns associated with localization of the freedom, which are marked by an area law scaling or sub-volume law scaling of the entanglement entropy. Now, what you've seen from the Zinn effect is that measurement offer the same kind of competition between unitary dynamics and measurement trying to localize the state. So the natural question to ask here is whether measurement can induce this kind of physics and whether there is two-phase transition induced by measurement between an ergodic, let me call, or volume law scaling of the entanglement entropy and an area law or localized phase. So what I will start to discuss is the original model. This has also been discussed briefly by Michael in his previous talk. This is the original model in which this kind of physics has been presented. So what do you have? Let me start with the system with unitary dynamics only. And instead of thinking of an Hamiltonian, we think of this in terms of unitary circuits. So the model works like that. You take two consecutive spins and you couple them by some unitary evolution, and then you take the next pairs of spin and you couple them by unitary evolution, all in parallel. After this first elementary step, you just repeat, but you alternate the spin which are coupled, the pairs of spin which are coupled by the unitary evolution. Why you do that? On one end, this can interpret as a quantum circuit. On the other end, if you think of very long time scale, this is nothing but a trotterization or approximation of the unitary dynamic, unitary evolution due to any local Hamiltonians. In order to keep it also general and not being specific of a certain Hamiltonian, you have the freedom, now that you have determined the locality by coupling only pairs of spin at each time steps, you can take this unitary evolution to be completely random unitary matrix that couples to spin, which means matrix in U4. So what does it happen to the information, which is the entropy in these systems? This entropy will grow at a constant speed. So there's a finite velocity of spreading of the entropy across the system. And it reaches a state, a steady state, which depends only on the size of the system. If the system is finite size, and it will scale like the length of the system itself. So this is the signature of the volume law. So the steady state reached by the system scales with the size of the system itself. Now, what happens if we put measurements into this system? Of course, if we measure everywhere with projective measurements, the system is completely unentangled and entanglement entropy is exactly 0. Now, the question is, what happens if we measure with a certain frequency or with a certain probability for each of the spin? So we can measure some of them or not measure some of them, and we can do this by throwing a coin and choosing a measurement probability P. Now, the question is whether there's a critical P and whether there's a real phase transition, so a sharp transition in thermodynamic limit between the volume law and an area law phase. Now, the answer to this question is mostly numerical, except a couple of instances. One has been shown by Michael for free fermion. The other one is the case of so-called stabilizer circuits with in which the mode can be mapped to some perforation phase transition. The model we are studying here, we have numerical evidence that the transition exists. The point before I go to the results, I want to point out something quite crucial about this kind of dynamics. First of all, compared to many body localization in which the system is described by Hamiltonian, so you're looking at equilibrium properties of the system, or in this case, the system is intrinsically out of equilibrium because you're measuring at different times, so you're constantly driving the system by measurement at each time continuously. The other important thing is the role of measurement. So in this way, this is an open system because it's coupled to an external environment, which is constituted by a set of local detectors. The important point I want to make is that if you average over the detector readout, and this averaging has also been mentioned by Val in his previous talk, what you obtain is an effective Lindblad evolution of the system. Now, this Lindblad evolution of the system will generally be completely insensitive at equilibrium state about this entanglement transition, simply because, at least in simple settings, your steady state that you reach as an average dynamics will be just a trivial, completely mixed state for your system, and there's no way to extract entanglement from there. On the other hand, measurement allow you to follow each individual trajectory, namely you can keep the readout and follow the state evolution for each single readout. For each of such readout, you can read the entropy and then average over that. Okay, so it's crucial here that these are measurements, and the effect of the measurement does not induce any decoherence, but preserve the purity of the states. So how to characterize a transition? The few quantities one can look at. The first one is the scaling of the entropy. And other ones are quantities related to information, specifically the mutual information between different subsets, A and B, which is this bipartite mutual information, or the one which is probably most striking quantity to look at, one has proven to be more reliable to detect this transition, is the tripartite mutual information. This looks a bit complicated, but essentially, if you have large correlation, large entanglement across the entire system, this quantity is negative and grows with the size of the system. So it's larger and larger negative. While if you have an area low, this quantity is supposed to go to zero and goes closer to zero the larger the system. So a transition here can be determined by a crossing between the tripartite mutual information for different sizes of the system. But let me show this in practice. So this is the model, the original model that was studied, and this is how this quantity looked like. So what you see in the first two pictures, in the first two graphs, is the entanglement entropy as a function of the probability to perform measurement at each site. And what you clearly see are two regimes, at least qualitatively, you can identify for large probabilities. You see that different colored curves correspond to different sizes of the system. These are all numerical simulations. For large probability, all the curves collapse onto a single curve, which means that essentially this is independent of system size. While for very small value probabilities, you clearly see that there's a dependence on the size of the system for the entropy. Now, to extract quantitatively a transition point from here, there's a couple of ways. One way by looking at the entanglement entropy is to look at the maximum of the variance of this entropy. This has been used successfully for many-body localization. And the idea behind that is that the fluctuation of the entropy will be large at the point in which there is a transition between the two regimes, while they will be pretty low when you're very well inside the different phases. So if you are in the localized phase, what you see is that the variance is indeed small, and so is also in the volume law phase, and actually it's really peaks around the transition. The peaks are broad, but you can follow the maximum of these peaks for different value of the length of the system, and you can extrapolate as a function of 1 over L or 1 over L squared. This is an empirical choice here. You see that this extrapolates to a finite number in the thermodynamic limit. Now you can also use this. You can use this critical value determined this way to try and collapse, to perform a finite size scaling of the entropy curves according to the formula you see on top of the slides. And actually, indeed, the curves collapse rather well onto each other. This fitting as only one parameter, which is essentially the universal coefficient gamma, nu here. So from this analysis, you can extract to value the critical value of this transition, estimated this way, and a critical exponent for the scaling of this phase transition, which is reported here in the table. As I said, there are other ways to measure, identify this transition coming from mutual information. Now, they are slightly different if you look at specific numerical value. But given that we can only look at system of size of 20 or 24 at best in our simulation, in some cases, they are definitely consistent with each other. So the message is, in this system in which you have stroboscopic evolution and projective measurement, you can confidently say that there's a phase transition between a volume law and an area law of the entanglement scaling, and this is driven by the probability of performing the measurement. Now, the work we did, and I would like to talk more details here, has to do with the fact that measurements are not only projectives, and actually in most cases they are not projective measurement. It's hard to do projective measurements. So the question is, what happens to this transition when you go away from the projective limits? Does the transition still exist? You partially know the answer, at least in one setting from the previous talk. What I will do now, I'll try to give a bit more details about the model we use for measurement which are beyond projective ones. So we introduce this model of positive operator value measurement, and then I will go to continuous measurement. So this has been described in general terms by Yuval in his talk. By using a detector which consisted of a spin. Here we are measuring a spin with a detector which has a continuous degree of freedom. So instead of thinking of a detector like another spin, think of it like a pointer or a single particle that can move along the line. You can think of the original von Neumann papers and model about measurement for that. So you can think of a particle spin with z component is coupled to momentum of a moving particle, and the particle is initially prepared with a certain distribution around the origin of its x, the coordinate x. And now you let evolve, as you said, you let evolve the system coupled to the spin according to this Hamiltonian for a certain time. As a result of that, the wave function or the probability distribution, if you square it, of the detector changes. And actually, there are two cases in which it's very easy. If spin is up or spin is down, this kind of Hamiltonian, the only thing it does is shift the distribution either to the left or to the right by a given amount, which I'm calling here x naught, but you can generally define in terms of a parameter lambda, which can be the strength of this Hamiltonian or the duration of the measurement itself. So there are two cases in which this distribution is either shift left or right. If in general you have a state of the spin which is neither spin up nor spin down, you get superposition of these two wave functions corresponding to the distribution. So your distribution will look like the sum of two Gaussian picked around plus lambda or minus lambda, and the weight of these two Gaussians will depend on the state of the system itself. The measurement process works in the fact that you at some point have to read out your detector. So the detector in this context plays the role of an ancillary or auxiliary system, quantum system. So you read out this detector, and this gives you a specific value x of the position of the detector. And as a corresponding result, you update the state of the system. So in this state, you will change the relative weight of spin up and spin down according to the weight of the distribution P of x. So this is a specific model, and this model has two features. In case of lambda being, which is, as we call it, measurement strength going to infinity, this model reduces to a projective model in which the system is projected either up or down. But you have another limit you have another limit for lambda going to 0, in which measurement is extremely weak, and you perturb the system arbitrarily weak. The limit lambda going to 0, you're doing absolutely nothing to the system. Now, this fits in a general scheme which can be applied to essentially any measurement. So any measurement will be described by a classical readout, variable x, and this variable comes with a certain distribution. So the way in which theoretically we describe this is by a matrix M, which depends on the readout x and maybe by some parameters of the detector. It's a cross operators, technical language. So what happens once you know this matrix, you know everything about your measurement procedure. So essentially, this matrix determines the probability of the distribution of the readout given the system states. And once you choose a specific, once a specific readout is obtained in an experiment, this matrix also fixes the update of the state for that specific measurement readout. So we want to review what happened to them. How much time do we have? Well, I hope I have about 10 minutes. So what we want to do review is what happens to the studied interplay between measurement and.
About on time, but feel free to take a couple of minutes if you need to finish, but start closing.
Okay, so what I want to do is to review what happens to the physics we describe for projective measurement when the measurements becomes P of M. First of all, let's review what happened to the Zeno effect, and this also touched upon the question by Yuval in the previous talk. So we can consider a simple model here in which the possible readout are just two discrete numbers, 0 and 1, and there's a parameter Q that controls the strength of this measurement. So you have two cross operators, either M0 or M1, and they're controlled by quantity Q. Now the other step you can do here. So we're back to Zeno. So we have single spin, and we have an Hamiltonian proportional to spin in the x direction. Now, when Q goes to 0, this measurement, this operator M, when Q goes to 1, Q goes to 0, this operator is reduced to a weak measurement in which you barely alter the state of the system. So what you can do, you can turn this into a continuous measurement, where continuous means continuous in time, in the sense that you can take this parameter controlling the measurement to be weak, and you perform measurement at interval dt, and the strength of the measurement, Q, is controlled by the interval at which you do the measurement itself. When defined this way, the entire evolution has a continuous limit, which means the combined evolution of the Hamiltonian and the measurement have a continuous limit, dt going to 0. And if you analyze the xenodynamics in this continuous limit, what you see is that you can also identify a transition between a regime in which the system performs the oscillations. This is a complicated picture, but you can just look at the red curve, which essentially tells you what is the probability for the steady state of the system to occupy a certain point on the block sphere. So there's a regime for very small measurement strength in which the system has a probability to be essentially everywhere. As long as you increase the parameter lambda here, you see that the probability changes, and at the end you reach a regime in which a probability is strongly localized around either the North Pole or the South Pole, which is the Zeno regime. Now, in terms of these continuous parameters, that's not just phase transition, that's just a single degree of freedom, but there's a cascade, I would say, of different changes, qualitative changes in the probability distribution that can be marked as a transition. So a transition exists also in this continuous limit for the Zeno physics, and therefore it makes sense to ask what happens to these settings in the many-body entanglement transition we described before. So what did we do? We take the previously studied system, which is the circuit model in which we have the unitary dynamics between adjacent spins, and we keep the unitary to be completely random unitary Hamiltonian, and we intercalate this unitary evolution with measurements. So the elementary step of our evolution consists now of 4 steps. First, unitary is between, let's say, even and odd, measurement with some probability and some measurement strength, lambda over delta for all the spins. Then unitary between odd and even, so alternated compared to the previous partial step, and then measurement again, and then repeat everything forever. So we simulate the system, and here are 2 typical simulations of how the entropy changes in time. Indeed, you see this is the average half-cut entropy as function of time. You see a linear increase for a certain time, and then a saturation. And you can really check that the value it saturates here. This is for a rather small value of the measurement strength and for the probability P1. So in this case, we are measuring everywhere, but you're measuring with a small measurement strength. The reach value, and this value scales linearly well with system size, are ready for small system sizes. When the value of the measurement strength is large, what you see is that the entropy does not grow much. There's a lot more variance here, but it's very close to zero. And most of all, the average value does not scale or scale very weakly, only at small value of L with the system size. So these are indications might be there is volume in area law. The question is, what is the transition? Sorry?
Do you have much more to say?
I cannot hear what you're saying.
If you can
Sorry. Okay, I continue. Maybe. Okay, so what we can do, we can simulate the system and try to identify this transition. And the way we do is exactly the way you have seen in the previous slides. We looked at the entanglement entropy scaling and the maximum of the variance of the entropy. This is exactly the same analysis I showed you before. And these are the results you obtain for this system. You perform a data collapse, and this gives you a critical value for the probability, which agrees with the one in the previous model when you go to very large measurement strength. Or you can have the opposite regime in which the probability of measure is 1, so you measure everywhere, but you measure with variable strength. So if we perform this analysis for any parameter in this parameter space, what we can do, we can map the transition, the phase boundary, the phase diagram between the area and the volume law phases in the entire probability and measurement strength path. And the main result of this is that you obtain a critical, there's both a minimal probability, critical probability below which there's no way you can perform a transition to an area law, but there's also a minimum measurement strength below which you can never achieve an area law behavior. So you need both to measure with enough probability and with enough strength if you want to obtain this transition. The next step we took is to take this into the continuum limit. So what we do here, we take measurements which are done with no more in a stroboscopic way at finite dt, but we make the measurement frequent enough in times, and we scale the measurement strength accordingly. Now, this gives rise to a stochastic process, which can be parameterized by this Schrödinger stochastic equation, in which the role of the measurement is to induce both a nonlinear dependence on the state of the system. You see here in this average of the measured operator, and induce noise, which is Gaussian distributed. So this is a linear process. And on top of that, this is exactly the same kind of physics which has been studied for free fermions in previous talk. And this is the phase diagram that you've seen in the previous talk. But for free fermion, you have a transition between a constant scaling of the entropy and logarithmic scaling. What we are doing here, we are changing the Hamiltonian, and we are looking at systems which are essentially interacting. We have results for specific Hamiltonian, but rather than that, I would try to keep the random unitary setting of the evolution here. So what we have is a measurement, which is determined by this stochastic binary process. And simultaneously, we want to define a process which is stochastic as well, which is corresponding of a completely random process for the random unitary circuit, but for continuous limit. And we can do that according to a principle of maximizing the entropy at each point. So we use what's called Poisson kernel. So that's a transformation that uses a parameter mu to continuously bridge between a completely unitary random matrix and a matrix which is as well as possible as close to the identity matrix. So if mu goes to 0 and you scale mu as a square root of dt, what you obtain is a unitary evolution which is can be approximated as the identity minus some correction dt. So if this gives an effective Hamiltonian, which depends on the matrix B, and this effective Hamiltonian will have a certain distribution, which is dictated by the randomness of the completely random operator B. So we analyze also this continuous model, and what we find is that also in this continuous case, the transition persists. So if you have a system which is continuously measured in time with a P of M of arbitrary strength lambda naught, you still find the transition, and transition is between an area and a genuine volume law. So we analyze this with usual analysis with the entropy that I reported before, but we also performed analysis in terms of tripartite motor information and the processing, and both results completely are in good agreement and produce a certain value of the critical strength. Now, I have only a few comments I want to make here, and I want to say how universal is the behavior of this transition in the continuous measurement setting. So the good point of our model is that you can continuously tune a parameter to go between the stroboscopic and the continuous measurement, still in the P of M scenario. And what you can see is that the behavior of the transition is rather universal across the entire crossover between the two regimes. In particular, what you can see is that if you take a very small value of lambda, definitely below 0.4, you see that all the curves show exactly the dependence. The L dependence of the curves changes between the stroboscopic and non-stroboscopics. And this is the same for all the value of mu. The other thing you can notice is that if you take some snapshot of the entropy and its variant depends at different points across this crossover between stroboscopic and continuous measurement, they present exactly the same qualitative features. In fact, this goes even further, and you can notice that what I plot here is the entropy dependence and the variance for three different cases: the totally continuous measurement case, the stroboscopic case but with variable measurement strength, and stroboscopic projective model. And you can really see that the behavior is rather universal in all this model, and the critical point can be also mapped to each other upon precise scaling in terms of an effective strength, which depends both on the strength and on the probability of performing the measurement. Now, the last observation about universality is that while the critical exponent can continuously be bridged between stroboscopic and continuous measurement, the needs different in terms when you go between projective and P of M measurements. And this you can clearly see in the extraction of the critical exponent. So the critical exponent of the continuous and stroboscopic P of M measurement are pretty close to each other. These are finite size scaling with very small numbers, so there might be finite size correction to the value, but this might correspond to the same kind of universality class. But these are very different from the critical exponent obtained for projective measurements dynamics. So it might well be that transition happening in continuously P of M measured system might be a different universality class of that obtained in random circuit with projective measurements. And with this, I think I can conclude. So what I showed in this talk is that measurement can induce a phase transition between an extensive scaling volume law and a localized scaling area law of the entanglement. This transition is controlled both by the probability of performing local measurement and by the strength of the measurement. And the transition persists in the continuous limits of the measurement. Now, the crucial point is that we don't know yet whether these are how universal are this transition. We know for sure that in this big class of models there are different phase transitions, which are certainly different from each other. The transition in free fermion is different for sure from the transition in stroboscopic model, both with continuous and projective measurement. And also the transition in stabilizer circuits is also can be mapped to a percolation transition, and this is also different from the one in stroboscopic measurement. So there's a collection of different transition between entanglement and area law, which we just started to explore. And the plan is to continue the exploration of this physics. With this, I conclude my talk. If you have questions, I'm open for that.
Okay, thank you, Alessandro. I apologize for Kirilla, he misunderstood the time scale of the talk, but
I hope I'm not too off.
let's thank the speaker. So any questions? Please, Yuval.
Hey, Ale, nice talk. You mentioned half implicitly the fact that the entanglement entropy transition, area law to volume law, may be related to a transition between localized to non-localized phase. And if I interpret this localized to non-localized transition in a broader meaning, I put some perturbation on one endpoint, in one endpoint of the system, and I'm trying to see if I can detect something in the other endpoint. Is it clear that the entanglement transition and the localization, delocalization transition should occur at the same point or the same transition?
It's not obvious, and I don't have direct data about that. No, it's not obvious that there's a single transition there. The transition in the entanglement should necessarily correspond to the transition in the transport of excitation or densities, conductivity or electricity, if you want. There can be different transition.
For example, I can imagine a very simple system, just a ferromagnet.
Yeah.
You know, Heisenberg ferromagnet, which I think would correspond to an area law, but still that would be completely delocalized. I put some perturbation on one side, and there will be a spin wave propagating to the other side of the chain. So
your Hamiltonian is disordered. What are you? Let's be more specific. You have an Heisenberg.
No disorder. I think that
that's a volume law. If you don't put any disorder, this is a delocalized phase from the point of view of entanglement in the Heisenberg chain, right?
Yes, but now I'm trying to play with disorder, and I'm asking whether the two transitions should take place at the same point.
So we looked at something. We didn't look at the transport of excitations across the system, but I stick to the previous answer. I cannot confirm that the two transition in terms of entanglement or in terms of transport of excitations occur at the same critical value.
Okay.
What I can say is that we studied the propagation of entanglement in a system like the one you mentioned, which is an Heisenberg chain, which is subject both to disorder, static, and to noise, which means local fluctuations in the Hamiltonian. And on top of that, we put some noise. Okay, so what you get is an Hamiltonian, which is deterministic. There's some noise that mimic the idea of fact that you have some random local Hamiltonian, and you can have some disorder. Now, what you see, these are just ways that show you can characterize a transition, but actually what you see is the transition of entanglement depends on both the static disorder and the dynamical disorder. So probably to answer your question, this is the best picture. If you look on the left, or the lowest panel C of the left figure here. So what you see here is the transition point determined for the entanglement transition as a function of the disorder strength. So in this model, if you look at the x-axis, you see there's a dashed line, and that line is the value corresponding to the MBL transition, okay, which is localization transition you're talking about. And what you see here, you see that the different points here corresponds to different disorder noise in the system. So what you actually see is that if you're making the system more and more random, less and less random, if you make the system less and less random in terms of unitary dynamics, it seems you cannot perform this further because we don't have enough data for that. But if you look at this guide to the eyes, which maps the crossing between adjacent value of different disorder, you see that this is compatible, at least, with the MBF transition. So I cannot give you a conclusive answer, but I mean, the two transitions should be close to each other.
Okay, thanks.
But this is all numerics, so I'm afraid I cannot give you
Okay.
an answer to that.
Okay, thank you, Alessandro. Can I ask you
Yes.
one small question?
Mm-hmm.
Could you please show intensity plots for entropy?
This one.
Yeah, this one.
Mm-hmm.
So could it be that this line of the highest intensity, or the region of highest intensity, is due to the quantum limit of measurement, when you have a constant action equal to Planck constant? So you can big uncertainty in the measurement time and small uncertainty in lambda, or
Yeah.
otherwise big uncertainty in lambda and small uncertainty in time. So can it be translated?
I don't think that this has to do with the quantum limit or the efficiency of the measurements, simply because in the model I'm taking, all the measurements are perfectly quantum limited. So I'm always assuming that my detector are all in the quantum limit, perfect quantum limit regime.
But you have a sort of concurrence between lambda and time. Time determines the blocks of unitary evolution, while lambda, it seems lambda determines projectors of your measurement. So you have interplay in your protocol.
So
is it true?
In my protocol, there's only lambda. In the measurement protocol, there's only lambda that sets the time, both the time scale of the measurement and the acquiring information of the detector. There's only one parameter that sets both. Okay. So this is exactly in the quantum limit. So I think that, and also, I mean, this plot you see here is not a plot of the entropy, but it's a plot of the variance of the entropy. So what you're really looking here is the region in which the fluctuation of the entropy are large, okay, which is the region in which the transition between the two regimes occurs.
But it can be due to quantum fluctuations.
Yeah, it is due to quantum fluctuation. Everything here is quantum fluctuation.
Okay, thank you.
Thanks.
I think we can discuss it further after lunch. And this concerns other talks. And now let's thank all the speakers of all previous speakers. And now we have coffee break. And after coffee break,
now the coffee break is over, and we direct the coffee break.
Okay.
And,
I didn't hear you.
Yes.
Here for this session, who's just coming here. This is Christina. She is going to share the next session.
Thank you for the introduction. So the next talk, let's introduce the next talk. The title of the talk is Measurement of Charge Qubits by means of quantum point constant surprise from interacting electrons. The speaker, Gleb Skorobagatko from Institute for Condensed Matter Physics, Ukraine. So you're welcome.
Okay, it's me. You open here. Okay, thank you, Kirill. Well, okay. Do you hear me? The people in the Zoom, do you hear?
Yeah.
Yes.
Yeah.
Yes.
Okay. Okay. Okay, let's start. Christina just told the title of my talk. And since our conference is hybrid, in a sense, my talk will be hybrid too. It consists of popular introduction and more specific, more special part with concrete results. So outline, there is outline of the talk. I will speak about charge qubits and about the subtleties of quantum measurements of this charge qubit state by means of many body systems such as quantum point contacts. And since we have one dimensionality often in this system in the systems and low temperatures, the interaction methods, the electron-electron interaction method in such places, and we briefly touch some consequences of this electron-electron interaction. So, but before to start, I would like to make a brief introduction for those people who didn't listen my yesterday's talk. It's about my story briefly and story of physics, theoretical physics in Ukraine. I originate from Kharkov, from Landau School of Theoretical Physics. And you can see a picture of the Kharkiv Center, which is a nice city. And then I had experience in Free University of Berlin. It was amazing 2 years in Dublin in the team of Alessandro. We did our common project, quantum detectors, where I was introduced in this topic. And then I came to Lviv to the Institute for Condensed Matter Physics, which is an example of Bogolyubov school, also famous school of theoretical physics. And you can see some nice pictures from Lviv. And here I have 2-year research grant and a small laboratory where we continue with Taras, Tak, and Vasilij. We continue to study different aspects of quantum interaction, which can be treated as quantum measure. So now I will start my introduction, and all these problematics concerns interaction between qubit and quantum detector, which is typically a many-body quantum system. So the problem with qubits, the most important and fundamental problem with the qubits measurement and preparation is that interaction between quantum system and another system is quantum as well. So, and that is why quantum objects experience strong quantum fluctuations at low temperatures typically, and that's why the interaction is uncontrollable on the macroscopic level. But macroscopically, if you use many-body system as quantum detector, so the averaged signal can be classical, and for example, quantum point contact can be used, and they are used actually in modern experiments. They are used as good quantum detectors for the state of Church-Q. What is, so this is also nice topic of modern research. Here you can see a picture from the conference on quantum measurement, and all previous talks are also evidences that this topic is important. And now what is what lies in the core of this problematic is experimentally. So here you can see what is the charge qubit. So you see here the nanoscale sized picture, nanoscale sized device, which is constructed as a quantum double dot, is two-island droplet with tunneling between these two quantum dots, and external gate which modify chemical potentials in the vicinity of this droplet. So, and one can control this, in principle, the state of this droplet by means of these gates. And here you can see on the left hand side, you can see a quantum point contact, two leads and tunnel junction. Tunnel junction here, which also interacts with electrons on this droplet. It's supposed to say that this droplet can be prepared in the Cologne blockade regime, that this regime where you can all the Coulomb forces from all electrons are compensated by external gates except one electron, and effectively you can prepare here one electron state on this droplet, which is delocalized along this droplet in general case, but also you can prepare by means of this gate the state where electron is concentrated more on the left on the left quantum dot or on the right quantum dot. These two dots are on different distance from the quantum point contact, and Coulomb interaction between electron which tunnel through this tunnel contact and the electron on this double dot depends on the state of the electron on this double dot, and this structure represents a charge qubit. So you can determine here two quantum states. One is say state one is when electron is concentrated here on the left quantum dot of a droplet, and say state two when it concentrates on the right quantum dot. And but there is also the third of two states, 1 and 2, and these states of electron here determine the interaction between tunneling electrons and this droplet, and this interaction affects the tunnel, the height of tunnel barrier here.
I'm sorry. The sentence about this third thing was cut by Zoom. So could you repeat, please? You said there is a third something. There are two states, and then there is a third something, and it was missing.
Okay. So what was the last information you heard? You have heard?
Well, you said there is one state concentrated on the left, one state concentrated on the right. That's clear. And then you said there is a third, and then it was a black hole.
Yes. There is a third possibility when the electron is delocalized on this droplet. And this can be treated as a quantum superposition of state 1 and state 2. And all these three possibilities affect differently the tunnel current through this junction. And so if one is able to measure the tunnel current, then after the measurement time, the period of measurement, she collects the statistics of charge transfer through the junction and measure in such a way a tunnel current through the junction. And this tunnel current, average current, will be different dependent on the height of tunnel barrier here, which is affected by the state of electron here due to Coulomb interaction between the island and the tunnel contact. And as I said, this interaction affects both counterparts of this system. So qubit affects tunnel barriers and modifies tunnel current through the junction. But there is a back action. The electron in tunnel contact also decohere the state of the electron here if the state was quantum superposition of state 1 and state 2. And this as a decay of radial oscillation of this two-level system, which is a charge qubit. So so what is the mean effect in this measurement dynamic? So here you can see the sketch, stroboscopic sketch of how one determines that by means of tunnel current that the qubit is in the state 1 or in state 2. So one can repeat the same tunnel measurement many times to obtain the distribution of tunnel current with a certain average value. And if one stops the measurement at short time after the beginning of observation, then one sees this double peak structure with uncertainty region, where one cannot say in which state quantum dot is in the moment of end of measurement. So if one enlarges the time of tunnel measurements, so this region decreases, and after a considerable time, which is of the order of or which is connected to the qubit decoherence time, he finally obtains a pure picture of two separate distributions. So, and this what experimenters obtain from the tunnel current measurement on the left picture. On the right picture is schematically shown the true decoherence of a spatial wave function of electron on the double dot. So this is a schematical picture of true decoherence process. So, and here you can see that this true decoherence occurs faster than experimenter knows about it. This is just because the many body nature of the detector. So the quantum system, single quantum system, decoheres much faster than it takes many body system to fit this change of quantum state, qubit quantum state. So it concerns, and one has here two characteristic timescales. Here on the right picture, one can speak about the coherence time for charge qubit, and here on the left picture, one can speak about so-called acquisition of information timescale, where it's a time needed to acquire information about such coherence. And acquisition of information time is normally much bigger than through the coherence timescale, just because, in a sense, interaction affects asymmetrically qubit and many body systems. But there is a quantum limit of measurement, and these two timescales are equal. This is the ideal measurement, and one have no delays. So the experimenter in quantum limit of measurement knows acquire information about qubit state. At the same time, the qubit decohere to this state. So, and this is a very approximate description of problematics we are interested in. So here there is a formulas on about how one can estimate this acquisition of information time scale, which is the inverse time scales are such that the acquisition of information rate is always lesser than the coherence rate. And here is another picture of the same model, where you can see quantum point contact and charge qubit here with interaction. It's from our article with Alessandro. And here you can see that dependent on the state of charge qubit, the height of the tunnel barrier will be different, and the tunnel current will be different. But as for these time scales of the coherence, here you can see these graphs where Q is quality of quantum detector. So the Q is the ratio of the through the coherence time for charge qubit and the acquisition of information time for quantum detector for tunnel contact. And you can see that increasing the non-equilibrium in the system by increasing the bias voltage here, one can achieve a quantum limit of detection where Q tends to 1. And temperature spoils quantum detector due to thermal fluctuations. So if one increases temperature, this quality of detector dramatically decreases, practically to 0 at high temperatures. This means that in this limit, through the coherence time scale much smaller than the acquisition of information time. So, but what happens in the 0 temperature limit? Then detectors, quantum detection is good enough. It turns out that one can extract some new information about what happens on this scale, especially about the interaction-dependent instability in quantum detection due to electron-electron interaction in quantum detector. So schematically, is the idea is shown here. So one has here a charge qubit, which is controlled by the gates and the quantum point contact. And in bosonized language, which I touch a bit later, electrons in the tunnel junction form collective plasmonic quantum state, which is described by Latinger liquid model. And this collective quantum state dresses the quantum state of charge qubits. And this dressing happens in such a way that if initial state of a qubit was superposition of two base states 1 and 2, then this dressing results in the coherence of this superposed quantum state charge qubit. And the back action from the qubit affects the, as I said, affects the tunnel current through the junction, resulting in the interaction effects in the acquisition of information. And one can consider the detector efficiency in such a situation, how electron-electron interaction affects detector efficiency. And this was the subject of our study with Alessandro, and later by myself, where I arrived to this graph at low temperature regime. So this is the simple enough graph where the quality of quantum detector is a function of interaction parameter in Latinger liquid leads. So one can treat this as a measure of electron-electron interaction in the leads. So the bigger the G is, the G is between 0 and 1. It corresponds to repulsive interaction in the leads, in one-dimensional leads of the tunnel contact. So the bigger G is, the smaller the interaction is in the lead. So here, when G is equal to 1, it's a Fermi liquid limit. And in opposite case, at very small G, one has a situation of very strong repulsion between electrons in the leads. And one can see that quantum detection properties with such quantum detectors change dramatically with this interaction parameter. And surprisingly, for interacting system, one has good enough quantum detector properties of such contact, just because strong correlation between electrons in the leads, which facilitated the information transition about the coherence of qubit. And here the situation is much worse for weak interaction. But the most important thing here is this region of instability, where strictly speaking, the quality of quantum detection is ill-defined, or it changes drastically from very good quality to very bad one. And in this region, one can estimate, it happens approximately at G equal 0.7 or 0.6. And this is from this paper. And surprisingly, in some experiments with charge qubit, people see that characteristic timescales of charge qubit decoherence in experiment turn out to be the observed timescales of decoherence turn out to be much longer than it was expected before. So, and very plausible explanation is that the leads of tunnel contact were not completely non-interacting. So they there was an interaction in these leads. Then one at low temperatures, one can be in this region of quantum detection instability, which misrepresents the true decoherence time scale in the system. So there is another experiment with a similar results. Okay. Well, I will skip the technical details of bosonization, and I only can probably I will comment in more details on this result on the in-depth session. And what I want to say here about the physics is that bosonization method allows to reveal some features of non-equilibrium dynamics of tunnel current in quantum detector, which can be interpreted as the formation of non-equilibrium of non-steady which can be interpreted as formation of so-called steady floor state of plasmonic excitation delocalized along the system, which occurs much faster than the formation of steady state of tunnel current here. And another consequence here is that all this theory allows to build so-called tunneling maps of interacting electrons. Just if one calculates generating functional in the terminology of full counting statistics, then it can be translated in the language of distribution of tunneling electrons, which depends on the number of electrons tunneled through the junction and time. And here you can see intensity plots of tunneling probability. This is the probability for electron to tunnel for during time t, which is x-axis, and the number of electrons which can tunnel are on vertical axis, and the intensity shows the probability. So you can see the region of the highest probability on the small time scales, and the angle of this. So different pictures are describe different thermal situations. So here you can see high temperature regime where due to thermal fluctuation the picture is smeared. But here you can see a more clear picture at low temperatures. Then this angle describes this length is constant in time, and this angle is roughly speaking n divided by t, number of electrons divided by t. It's average current, and it's constant as it should be. But dependently on electron-electron interaction, if we increase electron-electron interaction, we decrease, the current is decreased, average current is decreased. It's well-known Kane-Fisher effect. But interesting thing here is this bright region, which refers to region of anomalous tunneling, anomalously high probability of electron tunneling on short time scales. And it turns out that comparing the size of this anomalous tunneling region for different Latin liquid parameter values which are close to each other, one can extract this difference between this small difference in Latin liquid parameter values from the comparing the width of this anomalous tunneling region on tunneling maps. And only parameter one needs to know here, except this width, is bias voltage here. And this is a way, possible way to estimate more precisely the small differences in Latin liquid parameters from the experimental data, just because normally in tunneling experiment, it's hard to estimate precisely the value of this Lagrange parameter, the value of electron-electron interaction. And physically, this phenomenon should be referred to so-called self-equilibration phenomena, which I commented briefly before. So the formation of steady flow regime beyond the steady state. So this approximately all physics what I wanted to tell, and I had to skip here the all theoretical details, such as details of the model, and this description can be shown in in-depth session in more details. So the main consequence here is that sometimes the collective dynamics of many particles, quantum dynamics of many particles, such as dynamics of electrons and quantum detectors, make surprises doing the simplification job in the sense of self-equilibration, formation of steady flow state. And one needs only to reveal this behavior. So it's basically all. And thank you for your attention.
Please.
Okay, so if I understand correctly, Gleb, you're saying that the destruction of oscillations in this double quantum dot due to a measurement is much reduced because of interaction. My sense of it is that this may be related to the monogamy principle of entanglement, namely the effect of detection has to do with entangling the detector to the system. But if the system is already entangled to some other degrees of freedom, it is much more difficult for the detector to entangle itself. So one can check your ideas by looking at the model where there are no interacting electrons, but you take another degree of freedom, a third degree of freedom, which is entangled to your double dot, and then you try to apply the detector. If indeed I'm right, the entanglement of, or entangling the double dot to a third degree of freedom will make life harder for the detector to undermine Rabi oscillations.
If I understand correctly, the thing is, for the case of interaction, the main effect here in the Lagrange liquid contact is Kane-Fisher suppression of tunnel current due so you need more time to observe, but because tunnel current is smaller than in the non-interaction case, but acquisition, so both time scales are smaller, are bigger, sorry. The time scale of qubit decoherence due to interaction with Lagrange liquid quantum contact, just because the charge is smaller due to Kane-Fisher, charge density is smaller in the vicinity of tunnel contact. But the acquisition of information time scale is larger, much larger in the interaction case as well. So the ratio between two is questionable in the low temperature limit. And here it's shown that in the sense of the ratio, the behavior is like this. But of course, for interacting electrons, the time scale of observation and time scale of both time scales of decoherence and acquisition of information should be much larger than in non-interactive case. Is it is it what you're asking about, or it's a bit different?
Look, I don't want to go into we don't have time. Yes, I think you can hear me. I don't want to go into a extracted discussion. What I'm saying is that, of course, the physics of many body is more intricate and more complicated than just taking a single additional degree of freedom. But the advantage of considering a single additional degree of freedom which is entangled to the system is to demonstrate that this goes this way of extending the decoherence time. But I mean, we can discuss it at some other opportunity in private.
Please, Alexander.
Yes, I would like to ask, which is actually related to Yuval's questions also. In '98, Gershon and myself analyzed measurement of a charge qubit by a single electron transistor. And what we saw was that if this single electron transistor is in the Coulomb blockade regime, sorry, not in the in the sequential tunneling regime, then this efficiency is very small, so that the two times are very different. The acquisition time, as you call it, is very long. But if you go to the co-tunneling regime, then it actually becomes a quantum limited detector. So my question is whether there is some relation between your result and this result. And this degree of freedom which Yuval was talking about, it looks to me, in our case, was just this number of electrons on the central dot, which was an extra degree of freedom, which was entangled with a qubit. Thank you.
Well, I mean, wait a minute. So first of all, here this graph is for very low temperature regime. Here I will have a formula for this ratio, unfortunately not. So the problem is that, as I said, in answer of Yuval question, the both time scales are very big for interacting electrons. So both, and this concerns the low temperature regime, first of all. So both the coherence time scale and the acquisition of information time scale. And what I can say here is just that well, probably this this schematic picture will help. What I discuss in that article is that the physics behind this quantum detection by means of interacting electrons is very similar to the Kondo effect physics, in the sense that here the something like Kondo cloud forms, but this Kondo cloud is the certain certain collective quantum state of plasmons here. And it, of course, due to bosonization, the bosonization is the picture of bosonization is the same for interacting and non-interacting electrons. So you transfer from interacting fermions to non-interacting bosons with renormalized group velocity of excitations. But the difference is that, to say it very roughly and very very schematically, so if you put your G parameter as 1 for simplicity divided on integer n, then all powers in this in the inverse time scales. Inverse time scales can be treated as probability. So these probabilities of the coherence due to Kondo-like cloud formation are multiplicative in the end. So it looks like the formation of simultaneous formation or destruction. It can be, one can see differently, one can look differently on it. But there are several Kondo-like clouds forming simultaneously in the interacting case. And this can make in the strongly interacting case, this effect can slow down the coherence, because one can speak about the coherence of several Kondo-like clouds simultaneously, which is more rare situation than the destruction of only one Kondo cloud in Kondo-like cloud situation in the non-interacting case. So I don't know whether I answer.
Yeah, probably the relation. Probably, I mean, it's probably not so simple, but at least also some local structure, like a central island of a SAT forms also in your case, and maybe there is a relation, but it's really one needs a longer discussion. Thank you very much.
Okay, thank you.
So thank you once more for nice talk. So we have a break for lunch, and the next talk will be started according to the schedule. So it will be. So thank you all. The next talk will be started according to schedule.
So we reconvene at 3 o'clock Ukrainian time. Enjoy your lunch.
Which is in 2 hours, right?